record. All right, so welcome back. We are now in lecture number 4 for Math 140 Business. And today we are starting with chapter 3. And chapter 3 is on the extremely important normal distribution. Without question, the most important of all distributions in statistics. Chapter 1 was about visual displays and some basic definitions. Chapter 2 was about measures of center and measures of spread. And now we move on to chapter 3, which is our first distribution. So first, big difference between what we did before in regards to the previous distributions and the normal distribution. Previously, when we talked about distributions, we had data from some sample, and we made a histogram, and our distribution, whether it was a categorical variable or a quantitative variable, essentially our distribution was, these are the outcomes from my sample, and this is all how often each one occurred. If it was a categorical variable, each category, what percentage of the time. If it was a quantitative variable, we had classes in our histogram from here to here. And again, the question is how many times did each one occur? When we talk about the normal distribution, we're talking about a theoretical idealization of scenarios that occur throughout nature and throughout experimental statistics. When I say you're dealing with a normal distribution, I mean that the underlying representation of how often each outcome occurs has a very specific and distinctive shape. And you've probably seen this shape or heard of this shape by its other name or one of its other names. Normal is also called a Gaussian. This one is not the one you've probably heard of. The other name of it is a bell curve. And that's one that's you hear about out there in the world sometimes, a bell curve. And what a normal distribution looks like is you have your axis, and your distribution looks like this, which apparently is supposed to resemble a bell, although I've never really seen it. I don't know, maybe like, it's like a, and then you have like a gong, and this thing like, bounces and hits the bell and makes these big, like in The Sound of Music when they get married and the guys ding, 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 almost, no one's making any indications that they have any idea what I'm talking about. So I'm just gonna keep going and hate all of you. Okay, so this is the normal distribution. And the normal distribution goes on forever in both directions, but tapers off very, very quickly, so that it's getting closer and closer to a zero value the further out it goes. If you've heard of the term asymptotic, it's asymptotic to zero. It approaches zero without ever actually getting there. And if you look at the x-axis, if for example, I tell you that we have a situation where my axis might have that scale. What we're saying is as follows. Out of all possible values that I might end up with if I did an experiment, which value is the most likely value to occur? It's 100. Why? Because the distribution shape, the heights of my curve is a reflection for how likely that outcome is going to be. So 100, which is at the peak, is a very likely outcome. 85 is a somewhat likely outcome. 70 is a somewhat unlikely outcome. And the further I go from the center, the more unlikely the outcome is going to be. I want to share with you an app, not an app, but how do I make a new page here? Is it this? No, it's not it. Oh, plus sign probably, okay. We're gonna reference this many times throughout the semester in various capacities, but I wanna show you one thing from it for the first time. So in this applet, we basically have 8 shapes that we can set this applet to assume is going on in whatever example that we're looking at. Which of these 8 shapes would be the normal one?
5.
Of 5. And what it means is as follows. I'm going to ask this applet to do an experiment roughly 100,000 times. Now, if I do an experiment 100,000 times, I'm not going to get the same outcome every single time. But the outcomes near the center are significantly more likely than the outcomes on the wings. Would you agree with that based upon the shape of the distribution?
Sí, señor.
Yes.
Habla español. So if I go ahead and I tell this applet to do this experiment 100,000 times, what do you think the shape of the histogram is going to look like, at least approximately?
Like number 5, right?
Well, let's take a look. So it is generating lots and lots and lots of samples, and it's building the histogram as I go along. Does this seem, with 106,931 samples taken, does this histogram seem like it comes from a distribution that looks like a normal distribution?
Yes.
Yeah.
Yeah. Is it a perfect curve, a perfectly smooth curve? No. The distribution itself is an idealization. We're saying in a perfect world, this is the shape it should have. But if you actually do an experiment, the distribution itself is only giving you likelihoods. It's only telling you how likely a specific outcome is going to be. But at the end of the day, any outcome is theoretically possible. So I'm going to get a few zeros in there. I'm going to get a few hundreds in there, but most of them are going to be somewhere in the middle. And if I ask to do it again with the same underlying shape, it's not going to look exactly the same, but it should look like ballpark the same. So this one, again, you can see subtle differences. It's not exactly the same height. Even the sample size is different. This is 107,105. But again, it certainly follows the shape of the distribution. If I went to something like number 8, for example, if I told it to do 8, where it's very likely to get small numbers and very unlikely to get large numbers, and I said, do this 100,000 times, where do you think the majority of my histogram is going to be located?
Far left.
On the far left. Does that mean I'm not going to have anything on the far right?
Oh, you still will, but it won't compare to the main source of the data.
Nor should it, right? I'm going to have most of them on the far left. I'm going to have some on the far right. And again, we get a
skewed right.
Sorry, and this is skewed to the right. Exactly. Now, we're going to have a lot of use for this applet as the semester progresses. This today was just to show you the idea that a distribution is an idealization, And any actual histogram is going to be approximately a normal distribution, but it'll never be perfectly a normal. It can't be, because histograms, by their definition, have a certain width and a certain height, and therefore they're always going to have these little columns. You're never going to get away from these little columns. And the curve itself, the normal curve that we have here, these are not columns. But if I actually did a histogram, it might look something like, so I might get data that looks something like this, right? It's getting higher and higher as I go this way. It might not be perfect, but something like this, right? So I might get a histogram that closely resembles the underlying shape, but it's never going to be exactly perfectly the underlying shape. Does that make sense?
Yes.
Okay, so the normal distribution is the most important distribution. We will learn other ones as the semester progresses. But this is an example of what is called a density curve. So I want to define this example of a density curve. A density curve is, first of all, it's a curve that is always on or above the x-axis, and the area beneath it, now when I say beneath it, I mean but above the x-axis itself, is equal to 1. And these two conditions really make a lot of sense if you recognize that a density curve is representing the results of a histogram. For a histogram, could you have a negative number in any column? No. So
No.
if you can't,
it's not possible.
It's not possible. So if you can't have a negative column, then your curve can't be negative, because the curve is your approximation to a histogram. And if you add up all the likelihoods of being in every one of those bars of a histogram, it has to add to 100%, because every sample has to be in one of those bars. So if you add up all the probabilities of all the bars, it's going to be 100%. And since the normal curve, since this any curve is representing the probability of landing in a certain bar, then if you add up all of those bars, it has to add to 100%. Now, how do we calculate the area under a curve? Well, if it's a rectangle or a triangle or a trapezoid or a semicircle, that's easy. We could do that with geometry. This is none of those. This bell curve, the actual formula for this is something along the line of e to the negative x squared. E to the negative x squared, if you have your calculator graph it, looks like a bell curve. And it's got some constants hanging out in there, but basically it's e to the negative x squared. You cannot do that with geometry. So anyone know from their mathematical experience how to calculate the area under a curve? And you wouldn't know this unless you've taken the course. So it's basically saying, is anyone taking this course? Now,
You have to use the integral.
Yes, it's a calculus thing, okay? And even with calculus, this particular function is not doable by hand. And you could only do that with a computer or a calculator or some massive amount of approximation and work. Beyond the level of this course, don't need to worry about it. We're going to show you how to do it on the calculator, and it does it in seconds, what it would take you by hand hours. So it's very, very, very quick. But these two conditions, that a density curve can't go negative because probabilities can't go negative, and the area has to be 1 because the sum of the probabilities has to be 1. Those are the two things that define a density curve. And a normal distribution is therefore a density curve. Yeah, go ahead.
So is the density curve just like a way to present your data, just like a histogram, a pie chart?
Not exactly, because a density curve does not come after taking a sample. A histogram is what you do when you have a sample. The density curve is the idealization of the underlying distribution itself before you even take the sample. What I mean by that is as follows. Here's an example. If I do an IQ test and I ask 10,000 people, or not just ask, but I actually give an IQ test to 10,000 people, and I plot the results, that's going to be a histogram. And it turns out that that histogram looks very much like a bell curve. It has an average. Most people are near the average. And as IQ scores deviate from the average, whether down or up, the likelihood of them occurring goes down. You have very few people who are very, 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 very intelligent on the grand, the IQ scale. And you have very, very, very few people who are very unintelligent on the IQ scale, but the majority of them are somewhere near the middle. So a normal curve makes sense. Can we think, by the way, of any other measurements, anything else that we might take a sample from?
Could that be like height?
Yeah, like height.
Someone's height?
Yeah, so if you take a sample of height, most people are near the average, 5'8", 5'9", 5'7", whatever the case may be. And then how many people are going to be 6'5", 6'6", 6'7", 6'8", or 4'2", or something like that? It happens, but very, very unlikely, because heights quickly taper off on both sides to unlikely values. The histogram, thank you. The histogram represents the results of a sample. The density curve represents the underlying model that you believe the entire population follows. So when I say I believe the entire population follows a model of a normal distribution, what I mean is that even without an actual sample, the majority of them are somewhere around here, and it quickly tapers off in both directions. There's some average, there's some spread, there's some range, there's some IQR, there's some this and whatever. I might not know what those are, but I'm working under the belief that this model, this density curve, explains any sample that I might take and get later. So the density curve is an idealization. It's a belief of what any measurement might follow, whereas the sample is always a histogram, and therefore it's an actual, approximation to this idealization. Does that make sense?
So does a density curve, you only do it before you take the sample?
You don't even have to. You just go into a problem. In this course, we just go into a problem. We say, we believe that this particular situation is modeled by a normal with this mean and this standard deviation, and now go ahead and do some math. And you just assume that it's true.
So it's like, so it's just like the hypothesis of what you're about to do.
Exactly. Now, in a more advanced course, and it's certainly out there in the world, if I have data, I might look in this data and say, does this data come from a normal? Well, let me do a test to see. And there are various tests to determine whether or not it's likely that the data that you have actually comes from a certain distribution. And then if it does, then you can go ahead and do some math. In our case, we're just going to go and saying, this is normal, go calculate this. And you don't have to worry about it. Philip, you have a question? Sorry. Is that still Peter?
Somebody else.
Peter, still asking?
Yeah. So why does it matter though? If we're gonna take the data regardless, why do we care what we think it's gonna look like?
Well, that's a good question, and that's actually been talked about amongst the people who design the course and design which chapters are covered and whether or not density curves are a necessary component of the course. And it's been decided that from a more theoretical level, it's important to know what they are, even if they never really come about in practice. So I'm teaching what they're telling me to teach. But as we're going to see, we don't really need a really deep understanding of these. Just the idea, oh, this is normal. Okay, go do some math. Oh, this is a uniform. Go do some math. Oh, this is exponential. This is Poisson. This is this. This is that. Go do some math. And we don't really need to know too much about the underlying density curve itself.
Okay.
Okay. Philip, I thought you had a question earlier. I'm not sure if you still do or not.
I was just wondering, so would an example of this be like, let's say you're asking 1,000 people for their heights, and then the density curve would be you guessing that they'd be around 5'8"?
Well, I mean, in a real life situation, I might come along and say, I wonder if the average height is 5'8". So I'm going to ask 1,000 people. I'm going to get a histogram. I'm going to look at that histogram, and I'm going to try to model an underlying shape based upon the histogram, and I will fit my curve to the histogram, because the density curve is my idea of what life is, but the histogram is my sample. I can't argue with the results, assuming nobody lies or there's no distortion to the truth. So I'm going to try to fit my density curve to the model and say, okay, well, the peak of the histogram is here. So I'm going to guess that my density curve center is there, and the spread of the histogram is this. So I'm going to guess that the spread of the normal curve is this. And now here's my shape. And now I'm going to go and say, out there in the rest of the world, beyond these 1,000 samples, this is the curve that I'm going to be using. So I use my histogram to get the shape, and then I use the shape to predict things in the future. Thank you. Does that make sense? Armin, go ahead.
So can you say why we don't have y-axis if you, so for example, we're asking.
We will certainly have a y-axis because we will need to have a scale.
Yeah.
But at this point, I'm not worrying about that.
Okay.
Okay.
I have another question.
Yeah, go ahead. Go ahead.
So do we need to get the histogram first in
No.
order to do the density curve?
Well, in real life, yes. In this course, no, you won't have that situation. In this course, you will be told what to model it by and do not need to worry about it at all. You won't even need to draw the density curve. But there will be different situations throughout the course where I use the density curve to derive more sophisticated formulas. So you should certainly have an understanding of what the density curve represents. And as we go through today, you'll see it in action. Hopefully some of these questions will be further answered via example, where when you see it in action, you'll be like, oh, okay, that's how we use it. And that, okay, I get it now. So if you give me a few, hopefully it'll make a little more sense. Okay. So like histograms, density curves come in 3 basic flavors. So like histograms, we have 3 basic shapes of density curves. What word would I use to describe the first of those?
Normal, Bill.
It is normal, but
Symmetrical.
symmetric.
Yeah.
This is a
Right skewed and left skewed.
right symmetric, right skewed, and left skewed. So we've already come up with some examples of models out there in the world that we think we represented by symmetric normal graphs, like normal curves, like height, like IQ. Can anyone think of any situations in the world that might be modeled by either a right skewed or a left skewed graph? For a right skewed, that means very high chance of getting results from a sample of small numbers and very low chance of getting high numbers, whereas left skewed is very high chance of high numbers and very low chance of low numbers. So can anyone think of anything that might be modeled by one of those?
Ages of number of car accidents based on age.
Okay, number of car accidents based upon age. That's an interesting one. Which age do you think would have the most?
I think it'd be more symmetric, actually.
Well, hold on. Is there someone making noise over there? Or is that just me? All right. Which ages do you think would have the most car accidents amongst drivers?
Young and old.
Okay.
21.
So young drivers, 16, 17, they're new, they're inexperienced. They think they're invincible. Hold on, Amaya. I'm going to answer them in a second, and Alex, 1 second. But young drivers, get into a lot of accidents, and then old drivers get into a lot of accidents. But you don't really have that many old drivers in comparison. Most people, I think, when they get to an old enough age, they just stop driving. So I think that a right skewed graph would be probably more appropriate for age by car accident. But how about just age of death in general? When do most people die?
Older,
When
like,
they're old.
When they're old, right?
Yeah.
So if I just do age of death, certainly I'm going to have people dying of all at all ages. It's unfortunate, children die and teenagers and young adults, but the majority of people die when they're old. So if I was modeling age of death, I would probably use some kind of left skewed graph. And if I was modeling car accidents by age, that might be a right skewed graph. Where would I use these? As I mentioned, I took a few actuarial exams. The actuarial discipline is all about insurance and calculating likelihoods of events based upon whatever model you use. So these are all really serious questions because there's a lot of money on the line. I want to go through some of these things. Height of basketball players. Well, height of basketball players, if you focus only on basketball players, then certainly the average height will be further to the right. But I'm thinking it would still possibly be symmetric in that case, because amongst basketball players, you probably have the majority somewhere near around, 6'6", 6'7", and then very few who are short and very few who are tall. Muggsy Bogues and Spud Webb on one end and Manute Bol on the other. So you have very few who are out there. Amaya, you said ethnicity within a university. The problem with that is ethnicity is not quantitative. Ethnicity is categorical. And you need a scale to have a normal curve. You have to have, numerical values. So ethnicity would not work because it's not the appropriate type of variable. Someone sent me a text. They said COVID cases, but I need more than that. What do you mean by COVID cases? The age of COVID, people who die from COVID, the number who are getting COVID, and I'm not sure what you meant by that. So if you follow it up, I'll be able to answer. Someone else said left skewed could be the year of coins. Most people would have recent year coins, and less people, that's true as well. Most old coins are out of circulation. Either they're destroyed or people, save them or whatever. So the majority of coins that you come across will be, age-wise, will be a lot newer and fewer from, back in the day. Another left skewed example. The fact that we don't got to keep going, but the fact is there are lots of examples that you can come up with for symmetric, left skewed and right skewed. And just because it's symmetric, they're not all the same. If we go back to that thing here, let's look at these 8 curves that are here. Which of these 8 are symmetric?
Fifth one.
How many?
1,
Fifth
4, and
one,
5.
I see 1, 4, and 5 as being symmetric. 1 is the same everywhere, so it's certainly mirror image across the middle. 4 is basically the anti-normal. Instead of most of it being in the middle, most of it's on the wings. That might be your age of car accidents. Excuse me. And 5, of course, is symmetric. Which of them are right skewed?
That'd be 6, 7, 8.
6, 7,
3,
8.
6, 7.
Maybe
No, 3 also included here.
Maybe even 3, 6, 7, and 8. So just because you're right skewed doesn't mean you all look the same. There can be many right skewed graphs and many left skewed graphs and many symmetric graphs. It's just the basic idea of these 3 overall possibilities. Now, whenever we introduce something new, we want to relate it to things that we've done before. So let's talk about the median and mean and mode. So median, mean, and mode for normal curves. No, not just normal curves, sorry, for density curves. Now, in most cases, to calculate these things, you would need to do calculus. You would need to do actual math. So what we're going to do is going to be more qualitative. If you have a symmetric graph, like, for example, a normal curve, where is the mean located? Where's the balance point?
Center.
In the center.
Center. And where is the median? Where is the point at which half the data is below and half the data is above?
Center.
Also the center. So for symmetric, the median, the mode, the mode also, of course, the one that's most likely, we don't really have a sample to say which one is the most likely. The best we can do is which outcome is most likely. And that's going to be where the density curve is as high as possible. The higher it is, the more likely the outcome. So in the case of a symmetric curve, the mean, the median, and the mode are all essentially right in the center. What about a right skewed curve? Where is the mode located in a right skewed curve?
On the left.
More specific.
On the
Center to the
On
left.
the center left of the curve, that top part.
Okay, so the mode is right underneath the peak. So when it's right skewed, the most likely outcome is still where it's the highest. The mode has not changed. Where's the median and where is the mean for a right skewed?
It will be right here.
Again, what?
It will be in the lower point, like in the center of the lowest point and the highest point.
The lowest point, you mean all the way down here?
No. In the center of the highest point and the lowest point. Like, I mean,
like around there?
Yeah, like this. Yeah.
Okay, so which one, the mean or the median?
Median.
Okay, so let me see if I get this straight. You're saying if I divide up the area into to the left of the blue and the right of the blue, that there's 50% in each of those two areas, because the median is the point at which half the data is below and half the data is above. So are you claiming that those two areas are equal?
No, they're not equal.
They're not equal, so that can't be the median.
Yeah, it should be right.
Further left.
Well,
Wouldn't the mean be
here, tell you what, A, B, C, D, E, F, G. Which of those points is most likely to be the median?
D.
Okay.
D.
So you think D? Let's take a look at D. So D was about here or so.
I'd say it has to be a little bit farther down.
Closer to E.
Like E, yeah, I'm thinking E.
Okay, but remember we're doing this by eye and by hand, and it's not the easiest thing to do it to eyeball. But somewhere around here is certainly the median. It's the point at which half the data is below and half the data is above. The mean is the balance point. It's the point where if you actually build this construct and you try to balance it on your finger, it's where the mean is the balance point. Now, remember what we learned about histograms, same thing for normal density curves. Which is a resistant measure? Which is harder to change by having skewness, the median or the mean?
Median.
The median's harder, which means the mean is going to be pulled further in the direction of skewness than the median. So if you have a right skewed graph, the mean will most usually, in all of our examples, certainly, will be further to the right than the median. Whereas instead, if you have a left skewed graph, the mode is still going to be where the peak is, but now the mean and the median, so the median gets pulled to the left a little bit, not too much, but the mean gets pulled more. And that's just a qualitative understanding. On tests, you'll certainly have questions like, if it's a right skewed graph, then rank the mode, median, and mean. And you would say, well, the mode is less than the median, and the median is less than the mean. So mode, less than median, less than mean. That's the answer. Move on. Nothing further. Very qualitative.
In terms of Professor, in terms of the diagrams,
Yeah.
Is mode always going to be a dashed line compared to mean and median?
Again, these are just my pictures. The mode, the median, and the mean are points on your x-axis.
Yeah, I understand that. I was just saying in regards to that.
Yeah, so the mode is just this number. I just made I didn't mean to confuse. The dotted lines is just to show you that the mode is underneath the peak.
Okay, cool.
All right. Okay. So with that intro under our belts, now we can focus on the normal distribution. We've talked about normal curves in general, about density curves in general, symmetric, right skewed, left skewed, area under the curve is 1, where it's high, likely events, a likely sample result, where it's low, unlikely sample result. But now we really want to specify details of the normal, which we will be using pretty much from now to the end of the semester. A few times we're going to go into other topics, but for the most part, the normal curve will be here to stay. So a normal curve looks like this. Of course, as I mentioned, the normal curve goes forever in both directions. So how exactly can I model heights with a normal curve? Do heights go forever in both directions?
No.
No, but there's cutoffs for it.
Yeah, I mean, it's just a model. I just use it to represent my belief of the shape that my histograms are going to follow. It's not going to be perfect. And by the time it drops so small as to be essentially 0 anyways, I really don't care what happens past that. I really focus on the middle part. That's really what I care about. Now, where is the mean for a normal distribution?
The middle.
Right in the center, right? The mean of a normal is right in the center. We will use the symbol mu to stand for the mean of a distribution. Earlier, we used X bar to stand for the mean, but they're very different means. X bar is a sample mean. It comes from your sample. Mu is your belief in what the true unknown mean is. I don't know the average height of every American. I will never know the average height. If I tried to get out there and actually compute the average height of every American by literally asking every American what their height is, by the time I'm done, half of them will be dead, and I'll have a whole new slew of Americans to ask. There's no way I can ask every American. The best I can do is take a sample. The sample mean is X bar. I'm going to use the sample mean to guess what the actual mean is, mu, but I will never know the actual mean mu. But if I say you come into a problem and the mean is this, you use the math based upon the assumption that that's the mean, even if in reality, there's no way you ever can really know what the mean is. So the mean—
So mu is the population mean then, right?
Mu is the population mean, correct. It's the actual mean of the population, which I will almost never know. Now, we saw last chapter that if I deal with the median, I care about the IQR. But if I deal with the mean, I want the standard deviation. The standard deviation is a measure of how spread out the data is from the mean. If the data points are very far from the mean, I will have a high standard deviation. If the data points are near the mean, I will have a relatively low standard deviation. But at the end of the day, the standard deviation is just a number. Just like the mean is a number, oh, it's an average of 100. The standard deviation is just a number. And the question is, what is the number of the standard deviation for a normal? So here's the easiest way graphically to find it. If you look at this curve, would you say the center of the curve, the middle, the top, resembles more of a bowl or a hill?
A hill.
Certainly a hill. This was not a trick question. Certainly a hill, right? The center certainly looks like a hill, correct? And the wings, the two wings here and here, would you say they more resemble bowls, or at least parts of bowls, or a hill?
Parts of the bowl.
Or balls.
So here they're looking like bowls, and here it's looking like a hill, correct?
Spoon.
So the question is this: where, and when I mean where, I literally mean take your finger and say right there, point to it. Where on this curve do I transition from looking more like a hill to looking more like a bowl? Where is the exact spot where you would say, and again, we're eyeballing it here, so we might not all agree exactly, but where is the exact spot where we so I'm gonna make a bunch of dots or a bunch of letters: A, B, C, D, E, F.
Would it be 2
G.
points or just one?
Well, one on the right, one on the left.
Okay.
I would say either D or E.
I think
Okay, so we got a couple theories. We got
E or
a
I think
C.
A.
we got someone said B, we got an F. Let's put it in the
A.
A.
Yeah,
A?
it might be A. Because we're starting, the graph is starting decreasing in the A.
Oh, wait. Not decreasing. This entire area here is all like a hill,
D.
Yeah.
right?
Yeah.
So I don't start looking like a bowl till at least C, if not further.
Ah, okay, like that.
Okay.
So
Certainly past B and A. So again, it's an eyeball thing, but let's say somewhere about there. Is that a reasonable eyeball guess?
Sure.
Sure, why not? So the standard deviation is this distance. It's the distance from the mean. I said a bowl, yeah. So down here, it's like a bowl. On the side, it's like a bowl. And at the top, it's like a hill. So there's a point, one on each side, where it stops looking like a hill and starts looking like a bowl. Does that make sense, Jacqueline?
Professor, and what would those points be called?
Well, who's here has had calculus and can tell me what these points are called? Or has had
Break-even points.
What are they called?
Break-even points?
No, they're not
Break-even
break-even.
points?
They're not break-even points. There's no
The point of inflection.
point of inflection. So they are called points of inflection. For those who had calculus, I mean, when I say hills and bowls, it's not really mathy. The top we would say is concave down. And here we would say, you don't have to know this for this class, but there it's concave up. And the point of inflection is where it changes from concave down to concave up. And if you actually do the math, the calculus math, you can calculate that the point of inflection corresponds to the points of standard deviation. So if you go to the right or to the left, this is one ST dev to the right, and this is one ST dev to the left. So it's easy to eyeball a standard deviation for a normal curve by finding the point of inflection, which is where it's kind of changing from being bowl-like to hill-like. Yes, Philip?
I have a question. Does it go into percentages?
What do you mean, does it go into, what is the it? That you
Like when it goes left and right.
Well, I'm still not 100% certain what you're asking.
So you know how you said, okay, so there's the middle, and then you said one standard deviation left or right.
Yeah.
So would we say like one standard deviation to the left, or do we say like this much percent of the graph to the left?
We'll get into percent soon. But right
okay.
now, it's just we're this many deviations left, we're this many deviations right. So we will certainly get into percents very, very shortly. I mean, within a minute or two. But for now, we just want to calculate what is for a normal curve, what is a standard deviation? It's the distance from the mean, right or left, to these points of inflection, which is where the graph kind of changes from looking like a hill to looking more like a bowl, concave down to concave up. Now, does that make sense so far? Sure. Is it always from the median to the point of inflection, or only? No, this is only for a normal, not even for symmetric. This is only for normal. Okay, I cannot claim for other symmetric but not normal distribution. In fact, you know what? Here, let's do this. Let's do this. Let's go to 5 again, and let's draw a normal distribution. And because it's 0 to 100, I expect the mean to be about 50. Let's see what the mean is when it's done. Hey, look at that, 50. And what is the standard deviation as given in the picture?
18.4. So that's
18.4.
That's how much you add or subtract, right?
Yeah. So we're saying that if you go from about 32 on the left, which is about 18 down from 50, and you go 30, and you go to 68 on the right, which is 18 up from 50, we're saying that that should be roughly the point where you transition from looking like a hill to looking like a bowl. Does that seem eyeball to be relatively close to the true value? 50's right.
Yes.
Here, but yeah, okay, seems pretty good. Now, if I go to, let's say 1, now 1 is called a uniform distribution because it's the same height everywhere. And this is one where every number from 0 to 100 is as equally likely as any other number. So if I were to generate this histogram, what do you think it would look like? Approximately, at least.
Shoot.
A what?
Good question. I don't even know.
Well, I mean, what did 5 look like?
It's gonna look like a straight line across.
Be a big rectangle?
Yeah, it should look, I mean, if every number is equally likely and I generate 100,000 numbers, it should be somewhere in the line of each number appearing the same number of times, right? So let's generate it and see what we get. Does this seem like it's seems relatively accurate?
Sure does.
Sure does. So let's see what the deviation is here. Well, that's not about 18. So we see that first of all, I don't even see a point of inflection here. It's uniform, so there really isn't even one. So, but you see the deviation is a lot higher here. First of all, does it make sense, by the way, that the deviation would be higher for this than for the previous one?
Because the numbers on the far left and far right are skewing the deviation to go farther out.
Exactly. Remember, the deviation, the standard deviation represents how far the typical value is from the mean. With the normal, the majority of them are close to the mean, and very few of them are far from the mean. So the typical one is close to the mean. It's going to give me a pretty small standard deviation. This one, there's just as many close as there are far. So I have a higher percentage that are far from the mean. It's going to give me a higher deviation. Which one do you think would be even a higher standard deviation of the 8 that are given in the picture? Which one do you think will give the highest, actually?
4.
4?
I'm thinking 4. Let's see if it's higher than the 28.9 that we have here. Same mean, right? Same center, same average, but I expect a much higher, not much, but a higher standard deviation. We'll see what we get. Yeah, so look at that. We went even higher. Does that make sense? I hope. So.
Could you go over it like one more time? I'm so sorry.
Which part?
Why the deviation of 4 would be greater than 1, for example?
Well, because where are most of the data points located in 4?
In 4, it would be to the left and right.
left and right, but in relation to where the mean is located, are they close to the mean or are they far from the mean? Are the data points more likely to be close to the mean for number 4 or far from the mean?
Far.
Far.
Very far.
So the typical data point is going to be further from the mean for 4 than it is for 1 than it is for 5. And as such, the STDev for 4 is going to be larger than the one for 1, which is going to be larger than the one for 5. Make sense?
Yeah, makes sense.
All right. So everything so far has been, and by the way, just like we have a symbol for the mean is mu, we also have a symbol for the population standard deviation, and it is the Greek lowercase letter sigma. We've already seen capital sigma for sum. This is the lowercase letter sigma. We're going to be doing that a lot. So let's just compare and contrast. For the population, we have the mean is mu, and the STDev is sigma. And for a sample, the mean is x bar, and the standard deviation for the sample is S, or S sub x. Just notation-wise, very different because they mean very different things. So now, let's get a little into the math. We're still dealing with normal distribution. Where is the mean located? I forget.
Center.
Right in the center. Here's mu. If I go left and right, 1 sigma, then I have a very angry looking ghost. That's actually like the best picture I've ever drawn in my life. Anyways, so question for you, and do not answer this if you already know the answer. But we know that the total area under the curve has to be 1. Otherwise, it's not a valid distribution in general. So if you go out 1 deviation in both directions, what percentage of the total area under the curve is shaded, at least approximately? Again, don't guess if you've seen this before. But if you've never seen this before and you had to guess, what number, and you can put it in chat, what number would be approximate guess for the percentage of the total area under the curve that's currently shaded? 10%, 20%, 30, 50, 76.3, 90%, 12%. So I have 3 people say 50%. Anyone else want to venture a get? Someone already said 90%. A couple people said 90.
2/3.
I got 70, 2/3. I heard 70, 2/3. So they're pretty close to each other. So the true value, someone else says 75. The true value we actually don't get without calculus. So the best I can do is just give you the result that calculus would provide. It is approximately 68%. So if I go 1 deviation in both directions, approximately 68% of my data points are going to fall in that region. And let me center this better.
So does that mean that on average, when you go 1 standard deviation away from the mean, it's going to be 34% out, or covering 34% of the area?
You mean just like this part here?
Yeah.
Yeah. So 34% of my data points will be between average and 1 deviation above average, between the mean and 1 deviation above the mean. And 34% will be between the mean and 1 deviation below the mean.
Does that number ever change?
No,
Does it?
No, 68%. That's calculus. You can't argue with it. If it's truly a normal distribution, if it's truly normal, then about 68% of the data will be between one deviation below the mean to one deviation above the mean. If you want a slightly better value than approximately 68%, this is what my calculator gives me for, and I'll show you later how to do this, but for now, it's a little bit more than 68% of the data between one deviation and two deviations. Now, if I instead decide to go two deviations in both directions, 2 sigma and 2 sigma, then we know it's going to be higher than 68% because you don't have less than you had before. And you don't have 100% because you don't have everything.
97.
Someone says a 97%. Anyone else want to venture a guess?
78%.
So wait, as you're saying 68% was one deviation and we only added 10 extra percent going from 1 sigma and adding to the second one. All right, maybe it is 78%. I mean, I know the answer, but
I think it's 90%.
Yeah, actually it's 93 is 97.
so I got 90, 93, 97, 83. So the true
95.
So it's about 95%. And if you want, again, a slightly better approximation than 95%, this is what my calculator gives me for two deviations. A little bit more than 95%, 95.4 something. And we're only going to do 1, 2, and 3. But if I would go 3 deviations in both directions, if I go 3 sigmas in both directions, what percent would I have now? Approximately, at least.
A little bit less than 100.
Okay, it is a little bit less than 100. It is a little bit less than 100. It's about 99.7. And again, these results come from calculus.
And
now
that's
this
because too, question, is that because too you have outliers, right? Like you said before,
well,
there's certain data points that you're not going to kind of take into account.
Yeah, you're always going to have the exceptionally top and the exceptionally bottom ones. You're always going to have them. So there's a name for this rule. And I don't really understand where the name for this thing came from. It's one of those things in statistics that really makes no sense to me. But this feature is called the 68, 95, 99.7 rule. So if anyone could explain where that comes from, I'd be very happy to hear it.
Very bizarre.
Very bizarre. It's called the 68, 95, 99.7 rule. And it only holds for a normal distribution. Do not try to use it for anything that's not normal. There is a rule that you can use for any distribution. It is called Chebyshev's inequality, after the guy Chebyshev who came up with it. But we're not using it in this course. The best we have for normal is 68, 95, 99.7. Okay, so questions so far? Again, these numbers are results of just basic calculus. It's not even hard calculus, it's basic calculus, but it's again beyond the level of this course. So questions? Then I will ask you guys to do the following example. Up until now, it's been really a lot of lecture. Here are facts and facts and facts. But now that we have something that we can actually mathematically do, now it's time for me to give you guys an example to see if you guys can figure it out. So we have the following situation. We have some test that was performed in some place. The details are not important. But what we have is a situation modeled by the following. Now, this notation, capital N, parentheses, 6.84 comma 1.55. I'm giving 3 pieces of information in this notation. Who would like to guess what 3 pieces of information I am providing when I use this notation here?
The mean and the standard deviation.
What's the mean?
Dude, I guess 6.84.
0.84. The first number there is the mean, mu. What's 1.55?
Standard deviation.
The ST dev, that's my sigma. And what does the n tell me?
The n would be
It's normal.
That it's normal. The n tells me that I am dealing with a normal distribution whose
I was
mean
thinking about the number of points
Sorry?
like the other examples. I was thinking about the number of points like the other examples. You had x1, x2, x3, x4.
I'm sorry, say it again, please.
Remember how before the other day you were showing us the distributions where n would equal the total amount of data points you had?
Yeah, it's a completely different n in this case.
Okay.
Yeah. From context, you just gotta recognize. Yeah, quite often you'll use n or lowercase n. Usually, I use lowercase n for sample size. If I didn't, I probably should have, but I think I naturally do. You sure it wasn't lowercase n? In whatever example you're referencing, because I usually use lowercase for sample size.
I think it was capital was the n plus 1 divided by 2.
Oh yeah. For the number, yes, I did use capital N in that case. You're right. I did use capital N. In hindsight, I would go back and change that. But yes, you have to just know from the context what we're dealing with here. This capital N is just telling me that I'm dealing with a normal distribution.
Copy.
Okay, so I have a situation that is being modeled by a normal distribution whose mean is 6.84 and whose standard deviation is 1.55. And the question says, or a question says, what percent of my data points, of my data, will fall between I don't like the one in the book. I'm going to change it a little bit. So hold on. Between 3.74 and 8.39. So that's the question. What percent of my data, assuming that it is truly a normal of 6.84, 1.55, what percent of my data will fall between 3.74 and 8.39? I would like you to take a minute and to try to calculate this.
How do we calculate it?
Well, you would need to use the 68, 95, 99.7 rule and some imagination.
Cool.
Do you want answers or should we wait?
You have the answer ready?
I mean, I think it's one standard deviation, just 68%.
No, it's well, I did the standard deviations. The 8.39 is one standard deviation away, but 3.74 is 2 standard deviations away. So that's all the area in between that. So that would be what, 30 34 plus 34 plus 95 minus 68 divided by 2.
So someone did say the answer in chat. I've actually seen it a couple times. And the 3 times now, 4 times, I think maybe. The answer is 81.5%. So let's see why. The first thing I'm going to do is I want to see what I'm looking at. So I'm going to draw my normal curve. I know that 6.84. 6.84 is in the middle. And if I go 1 deviation up, what number do I get to?
8.39.
8.39. And if I go 1 deviation down, I don't quite get to 3.74, but if I go 2 deviations down, I do, right?
Yes.
Yes.
Okay, so I'm looking for the
Professor.
percent that falls.
Professor,
Yeah,
why is that?
why is what?
Why isn't 3.74 one standard deviation away? Why is
Well,
it 2?
What's 6.84 minus 1.55?
5.79.
Oh, I can't do that in my head. I'm not that good.
29.
What is it?
5.29.
5.29.
5.29. So 3.74 is not 1 deviation down. If I subtract another 1.55, that's when I hit 3.74.
Oh, okay.
It just happens to be 2 deviations down. Correct?
Yeah.
Now I know that this is 68% from here to here. I know that part 68%, but I got to add this little bit here to get the total amount. Correct? So the question is, how do I find this little extra amount? And I see a few people did it in chat, so I know that a number of you did it. But if you go to the 2 deviation rule, which is 95%, that tells you that if you remove this 68% here, how much is left amongst the 95% that has not been taken into account for that middle 68%? It's 27%. 13.5% for this part and 13.5% for that part. Which means we just take the 68% and then we add 13.5%, and that gives us a total shaded area, which is 81.5%.
So, Professor, like the 1 deviation, so like from 5.29 whatever to 8.39, that's 68%, right?
Mm-hmm.
Oh, okay.
And then it was a matter of figuring out how much we're going to add to that.
How much is yeah. All right.
Now, let me show you how to do it on your calculator. Everyone here have a TI-84? Anyone here have a TI-84?
I do.
Yeah.
I would like you to hit second.
Second.
So second. And then hit the vars button, because above the vars is DISTR, distribution. So that will take us to distribution. And then pick number 2, which is normal CDF. And then for lower, do 3.74. For upper, what's it going to be?
8.39.
8.39. For mu, what's it going to be?
6.8.
Can't see.
Can't see what?
6.89.
Mu 6.84.
6.84. And sigma, what's it going to be?
1.55.
1.55. And then you hit paste. And what paste does is it puts it in the stack. And then you hit enter. And it gives you 81.86%. Why is that not the 81.5% that we guessed?
because the 68% and the 13.5% are like approximations.
Yeah. They're only approximations. So 81.5 is a good approximation. 81.86 is a better approximation.
What does the CDF stand for after normal?
Cumulative distribution function. Because you are accumulating data from the distribution. So the cumulative distribution function.
So whenever you're solving for a certain area, you're only putting the numbers that you want covered.
Well, this particular example, the question was, what percentage of the data comes between this number and that number when the mean is this and the sigma is this?
Mm-hmm.
Those 4 pieces of information, it's all you need. Go to your calculator, bam, it spits out the answer. I don't need to draw the curve. I don't need to calculate how many deviations down or up I am. I just put the numbers in and let the calculator do all the work. So this is the first situation for the semester where, sure, you can do it by hand if you want, but it's just so much easier just to have the calculator do it for you. Does that make sense?
Yeah.
All right, so let's do another example from the same data. So another example, what percent of the data is, for example, I don't know, let's say above 5.29. What percent of the data is above 5.29? And you can do it by the calculator, but I would love if you first try to do it by hand and confirmed it with the calculator.
Wait, Professor, where did they get the 1.55 from earlier? Like for the
They gave it to you. This is all.
Oh, okay.
I'll assume it's all true.
So are we getting like the like from 5.29 and then past 8.39 as well?
Just above 5.29. I didn't say anything about a limiting point. Now, is that those answers there? Is that from a calculator or is that from by hand?
Mine is by hand.
Let me just do it on the calculator because I'm here. All right, so I do get. I have my calculator value, which is going to be a little off. So let me do it. Let me do it in my head. Okay, I got it. So those numbers aren't exact though. Interesting. Interesting. I mean, they're all close, but even by hands, I don't get exactly that. So I'm interested where you guys getting these numbers from. First, so I don't see the answer I have either from my calculator or by hand. So where you tell me where you're getting these answers from. They're close, but they're not exactly it. So someone explain. All these numbers are fairly close. So someone volunteer. Where are you getting these numbers from?
I did kind of the same breakdown that we did for the previous problem. So I
That's
just
what-
had
yeah.
So since I chose, since the 5.29 is one standard deviation to the left, that's 34%, and then I kind of just added the rest of the numbers up
Well,
as I went up.
but if it's 30, if this is 34% here, then
Then I
what's
added another 34.
no,
I kind of like added as I went up.
why? What's all of this in one step?
It was 97,
Wait,
99.7 divided by 2.
No. 99.7 is only up to 3. We're going
90.
forever. We're not stopping at 3. What's all of this in one step? All of this.
100 divided by 2.
50.
Yeah, it's 50%. It's like
50%.
half, right? It's the right half of the graph, correct? It's exactly 50. Not even an approximation. It's exactly 50.
So it's 84%, yeah.
Huh?
It will be 84.
So yeah, so it's going to be 34%. That's half of the 68 plus 50%, which is 84%. So a lot of these numbers are really close. I see 84.05, 83.85, 86.2, 83.85, 86.2, but I'm getting exactly 84. And even on my calculator, the calculator gave me 84.13%. So I'm thinking people, actually, I don't know what people did. That's why I'm confused. That's why I'm trying to pin it down as to where these numbers came from. But
where did the 34 come from? I'm completely lost.
Half of
I
68.
get the 50.
It's half of 68.
Okay. Because it's only one deviation, so we take the 68.
Yeah, it's just to the left, right? So if I draw this, if here's my graph here, then one deviation down, that's 34%. This is 50%. So since I care about all of that, that's just 84%.
Professor, you know how you made the breakdown of each standard deviation?
Yeah.
So I mean, it would be like how I got 83.85, and then if I add the outliers,
but that's
which would be 0.15, that would be the 84. So it's kind of more work than needed.
Wait, what 0.15? I'm confused.
It's the 68, 95, and 99.7 row, right? So then 100 minus 99.7 would be 0.3.
Oh,
0.3 divided by 2 is 15.
Oh, so you really broke it down like that. Oh,
yeah, that's what I was saying. I was kind of adding up the each kind of standard deviation.
Oh, you can do it that way, but wow, that's a lot of work.
Yeah.
That's half of 68, and then take 95 minus 68 and half of that, and 99.7 minus 95, and then half of that, and then half of what's left. Wow, hey, you can do it that way, but it's so much quicker just to say, hey, 50, 34, 84, done. Philip, you had your hand up a second ago?
And I was just saying the same thing he did. I just like cut it up and then added them.
Yeah, I mean, listen, again, you can do it that way, but the trick is to find the fastest way of solving a problem, not just a way of solving the problem. Does that make sense what I'm saying so far?
Yeah, so how would you put that in the calculator?
Oh, the calculator. So for the calculator, what would my lower be? And what would my upper be?
Lower is for sure is 5.29.
Lower is 5.29. What's my upper?
8.39.
Nope. I didn't say stop at 8.39. I said
infinity.
Infinity. So how do you put in infinity in your calculator? That's what I did. I just hit 9 a lot.
Oh,
whole bunch of 9s.
I just put 10.
10 would work because, well, actually, 10,
Well, I mean, I got 82, so it didn't work.
10 won't work because
10's below the third standard deviation.
Yeah, 10 is still pretty close. I mean, but 9,999,999, that's certainly far enough.
So as long as it's substantially greater than the third deviation.
That's right, substantially greater. So I just hit 9 a lot, and yeah, there's no infinity key that I know of on a TI-84. Maybe there is. I don't know. Every now and again, I'm teaching a class and someone says, oh yeah, you can do that by this. I'm like, oh my God, blow my mind. But I don't know of any infinity key. So I just hit 9 a bunch of times. So what I do is 9, 9, 9, 9, 9, 9, 9. Just a lot of nines. Does that make sense? Of course, you can do lower, you can do upper, you can do between two numbers, right? So all these situations. Now, this 68, 95, 99.7 rule only works if you magically land on numbers that are 1, 2, or 3 deviations below or above the mean. But what if I said, what percent is going to be between 3 and 4? Well, you can't do that by hand. But your calculator does it just as easily. Lower 3, upper 4. Here's my answer. I'm done. So the 68, 95, 99.7 rule is nice and all, but the calculator is even better. Make sense so far? Yes, no, maybe so?
I'm sorry, can you say which we can use any calculator we want?
I don't care what calculator you use. I just can't promise that your calculator can do it. I know how the TI-84 does it. I don't know how anything else does it.
Okay.
But if you have one that works, I don't care. Okay. Now, the next topic is probably we're not gonna finish it today anyway. And it's pretty much everything that's left in the chapter. So we're gonna hold it off for next time. So we did not finish chapter 3 today. So the homework for 3 is not due in a week or anything like that. You have plenty of time, but I would recommend getting started on it and not procrastinating. Anywho, any questions on anything that we did? Let's see. All those lovely people who started with their faces on camera, and I'm left with nobody or just one. Oh, I feel so alone right now. What can you do? Story of my life.